In various previous lessons, we have referenced out-of-order execution. Out-of-order execution is a CPU performance optimization technique allowing instructions to be executed as soon as their operands and the required execution resources become available, rather than waiting for prior instructions to complete in program order. Modern CPUs are superscalar, meaning they can execute multiple instructions per clock cycle across multiple types of execution units. These include ALUs, the arithmetic logic units for integer arithmetic and bitwise operations, FPUs, floating point units for non-integer computations, load store units for reading from and writing to memory, branch execution units for evaluating conditional jumps and branches, and SIMD vector units for processing arrays of data simultaneously. Instead of stalling on an instruction, waiting for a memory read or data dependency, the instruction scheduler and reservation stations inside the CPU's out-of-order execution engine scan for subsequent independent instructions. These components perform register renaming and dependency analyses to avoid pipeline hazards like read after write and write after write. Instructions are issued to appropriate functional units as resources become available. However, to preserve program semantics, the CPU must commit results in order. This is handled using the reorder buffer, which temporarily stores results of executed instructions. Once all prior instructions have executed successfully, their results are committed, written back to the architectural state, such as registers and memory, in the original program order. Modern CPUs are designed to be incredibly fast, capable of executing multiple instructions at once across different execution units. But just because they can run fast doesn't mean they always do. If a CPU had to wait for each instruction to fully finish before starting the next one, it would spend a lot of time just sitting around doing nothing. That's where out-of-order execution comes into play. Game changer for performance because it keeps the CPU busy even when things are stalled. Imagine you're baking a cake. I like cake. If you had to wait for the oven to finish heating before mixing the batter or wait for the eggs to cool before reading the next step of the recipe, then it would take all day. But if you can prep the next steps while something else is waiting, you finish a lot faster. So the CPU does that with out-of-order execution. If one instruction is stuck, it might be waiting on a memory fetch from RAM or a previous result. It keeps the CPU from sitting idle, looking ahead, finding independent instructions that don't need the stalled one, and starts executing them out of order. If there's no data dependencies, if it appears that it can be safely done, that's what it does. So out-of-order execution improves your pipeline utilization. Modern CPUs are pipelined. Different parts of the instruction lifecycle, fetch, decode, execute, write back, happen in parallel across different stages. And it's a great way to boost performance, but it only works well if the pipeline stays full. Without out-of-order execution, a single slow instruction like a cache miss could block the entire pipeline. We've discussed this a bit in previous lessons, and that would starve all the execution units. With out-of-order execution, the CPU can keep its multiple execution units, ALUs, FPUs, vector units, load store ports. It can keep these all busy, feeding them instructions that are ready to go, even if earlier ones are still pending. And this maximizes throughput and avoids bubbles in the pipeline. Out-of-order execution can hide latency. Memory is slow, especially when fetching data that isn't in the CPU's cache. So out-of-order execution helps hide that latency by overlapping useful work with long memory operations. While one instruction waits for data from main memory, several others can run in the meantime. And this is called latency hiding, and it's critical for making efficient use of CPU cycles. And most modern CPUs are superscalar. I like that word, superscalar. They can issue multiple instructions per clock cycle. That's what that means. But to actually achieve that, the CPU needs to be able to find enough instructions that can run at the same time without stepping on each other's toes. So this is enabled with dynamically analyzing instructions and executing them in whatever order respects the data dependencies. And that's what allows superscalar CPUs to hit their theoretical performance targets. It's what does enable increasing their performance. Without the out-of-order execution, the CPU would run instructions strictly in the order the software gives them, regardless if that means waiting unnecessarily. We've probably all sat there waiting in front of our computers, maybe something like this was going on. This would cause frequent stalls, especially in real-world workloads, like applications that mix computation with memory access, like databases and spreadsheets and data analytics. Code with lots of branching and unpredictable access patterns, and multi-threaded applications competing for shared memory. So in these cases like this, the CPU's execution units would often sit idle, wasting valuable cycles and dramatically reducing performance. So I think we understand now that out-of-order execution is one of the key reasons that modern processors are orders of magnitude faster than older, simpler designs. It's not just about raw clock speed. It's about keeping the engine running smoothly and constantly, even when some parts of the machine are waiting. Now, from a security perspective, it's important to understand that this performance optimization is also what opened the door to speculative execution attacks. Because executing instructions out of order means some instructions run before they're supposed to. And there's subtle ways that can leak information. And it's all about the information. Information is power, they say. So, although out-of-order execution is a performance feature, it plays a key role in enabling speculative execution, which can be exploited in side-channel attacks. With speculative execution, the CPU predicts branches and executes instructions ahead of time. If the prediction is wrong, the results are discarded, but side effects on microarchitectural state, like cache content, might remain. And then microarchitectural side channels, where attackers can measure things like cache timing, execution delays, and power usage to infer data not explicitly exposed by a program. While the architectural correctness is preserved, the microarchitectural behavior leaks information, and there's your critical cybersecurity risk. So we'll talk about some real-world exploits that benefited from out-of-order execution, speculative execution as well. We have Meltdown, which you hear about a lot throughout, especially the hardware sections of this course. Talk a little bit more about it here, and you can find details if you go look up online, type in CVE-2017-5754. Meltdown is a hardware vulnerability affecting out-of-order execution in modern processors, particularly Intel CPUs. It allows unauthorized access to privileged memory, enabling attackers to read sensitive data from the system's memory. Meltdown takes advantage of a timing issue, where the CPU starts accessing memory before it's confirmed that the access is allowed. By carefully crafting a series of instructions, an attacker can trick the processor into speculatively reading data from privileged memory regions. Even though these instructions are eventually discarded by the CPU, the access still leaves subtle changes in the cache, and those changes can be measured to recover the leaked information. Meltdown was independently discovered and reported by researchers from Graz University of Technology and Cybersecurity Technology and Google Project Zero in 2018. It's on the list of things that we would say yes to exploitation in the wild. Now, in other parts of the course, you might hear me say Spectre and Meltdown not exploited in the wild, but as we've discovered, there have been some malware samples found. Shortly after the public disclosure of Meltdown, the AV Test Institute identified 139 malware samples that appeared to be related to the Meltdown and Spectre vulnerabilities. Most of these samples were based on existing proof-of-concept code released by the security researchers, and that's how it goes. Vulnerabilities are found, reported, and attackers use those reports. The majority of these samples were recompiled or slightly modified versions of the original POC code. They were primarily used for research and testing purposes, and there was no evidence at the time to suggest they were part of widespread malicious campaigns. So we're in May of 2025 right now as I'm recording this, and the latest available information publicly released is that there haven't been any confirmed reports of Meltdown being exploited in large-scale attacks. However, the presence of these malware samples indicates threat actors were actively exploring that vulnerability. So that's why we will change from saying not in the wild to yes in the wild. So just take that with a grain of salt if you hear various pieces throughout the course, because of the fact that by the time you're taking this course, it could have been exploited a lot more. despite the mitigation factors that have been put into play. Meltdown primarily affects Intel processors manufactured since 1995, with the exception of Itanium and pre-2013 Atom processors. Some ARM-based processors are also affected, but AMD processors are not susceptible to meltdown due to architectural differences. Mitigations like kernel page table isolation, KPTI, are used. This is where operating systems have implemented KPTI to separate user space and kernel space memory mappings, reducing that unauthorized access risk. And microcode updates have also been applied where CPU manufacturers have released microcode updates to address the vulnerability at the hardware level. And software patches. Operating system vendors have released these patches to mitigate the effect of meltdown. Users are advised to keep their systems updated to ensure protection. You'll hear that all the time. While meltdown hasn't been widely exploited in the wild yet, that doesn't mean it hasn't by the time you've seen this video, but at the point I'm making it, the meltdown discovery highlighted significant vulnerabilities in modern CPU architecture. And we can expect the attempts are going to happen considering that we know attackers are already working to figure out how to really incorporate this vulnerability into their attack plans. Well, the rapid development of related malware samples does underscore that importance of timely patching and system updates, though. And Spectre, if you Google CVE 2017-5753 or CVE 2017-5715, you can get more details. And that's something you'll hear a lot, to be encouraged to do a lot, is look up the CVEs. It's actually, I think, very fascinating. Sometimes it's hard to read through them all, but it's a fabulous amount of information that both attackers and defenders are reviewing. Now, Spectre tricks CPUs into speculatively executing instructions that access memory outside of intended bounds, allowing attackers to infer secrets from other parts of memory space. You have the two main variants. Variant 1 is that CVE 5753 I mentioned, with the bounds check bypass using conditional branches, if else. Variant 2, the 5715 CVE, branch target injection via poisoning the branch predictor. In both cases, speculative execution causes the CPU to load secret data into cache lines, which can be probed with precise timing. It was jointly discovered by researchers from Google Project Zero, Graz University of Technology, and they had various academic and industry partners involved. It's been demonstrated in lab environments and partially observed in targeted attacks. So we can say Spectre-based exploits have been used in proof-of-concept demos and are suspected in advanced persistent threat activity. However, public detection of these attacks in real-world environments is very limited because Spectre doesn't leave obvious traces in system logs or memory. It exploits subtle timing differences that are extremely difficult to monitor using conventional security tools. So what's the honest truth? The honest truth is that just because something hasn't been discovered in the wild, it doesn't mean it's not in use. Especially when you've got something that's very stealthy. If you can't track it and you can't trace it, but it is a proven vulnerability regardless. Virtually all modern CPUs, Intel, AMD, and ARM, are affected. But Spectre is considered a class of vulnerability. It's not considered a single bug. That's an important distinction to make. Then we have Foreshadow, the L1 terminal fault. There are numerous CVEs you can look up to get more information on that. Foreshadow breaks the confidentiality of Intel SGX enclaves and other security memory regions, including kernel and hypervisor memory. Foreshadow exploits speculative loads that can bypass access controls and read from the L1 cache lines, even if architectural checks should prevent the access. By timing cache accesses, attackers recovered data loaded speculatively from protected areas. It was discovered by a variety of researchers. A couple of these are KU Leuven and University of Michigan. You have Foreshadow SGX. That's the Intel SGX enclaves target, breaking the confidentiality guarantees of Intel's Software Guard extensions, a hardware-based trusted execution environment designed to protect sensitive data like cryptographic keys, DRM secrets, or enclave secured code from being accessed by other software, even the OS, operating system, or hypervisor. So Foreshadow SGX can break that. The attack tricks the CPU into speculatively loading data from within an SGX enclave into the L1 data cache. Although architectural access to enclave memory is blocked, speculative execution ignores these permission checks temporarily. The attacker then uses a cache timing side channel, like flush plus reload, to infer the contents of the enclave memory by measuring which cache lines were touched. This effectively bypasses SGX's isolation, undermining its use in secure applications, digital rights management, and even some blockchain solutions. Then we have the Foreshadow OS and Foreshadow VMM. Foreshadow OS targets operating system kernel memory. Foreshadow VMM targets hypervisor and virtual machine memory. These are broader variants of the original Foreshadow attack. They demonstrate that not just SGX, but also privileged system memory, such as the kernel, hypervisor, and other VMs, can be speculatively read and exfiltrated. These attacks exploit the same speculative behavior, but instead of the SGX memory, they target kernel memory in Foreshadow OS and virtual machine guest memory and hypervisor memory in Foreshadow VMM. Attackers cause speculative execution of memory loads that should normally be blocked by privilege boundaries. The memory is accessed transiently by the CPU during speculation, and though it's later discarded, it influences the cache state. Using precise timing attacks, microarchitectural side channels, attackers deduce the values of these protected memory regions. Foreshadow OS could allow a compromised process to read sensitive data from the OS kernel, such as process credentials, kernel pointers, or security tokens. Foreshadow VMM could allow a malicious VM to read memory from other VMs or from the hypervisor, breaking virtualization-based isolation in cloud environments, which is a critical threat for multi-tenant infrastructure. Publicly, no one has confirmed any widespread exploitation in the wild of this. However, the risk was considered serious enough that Intel deployed microcode and firmware patches rapidly, so they put it at the top of their list, which means that they considered a serious risk, and we don't know if it was actually exploited or not, regardless of what we hear. Then you have Intel Core and Xeon processors, which are affected, and SGS enclaves are specifically affected, of course. Now we have zombie load. There are 4 CVEs associated with zombie load, so it's gotten some serious attention, right? It leaks data from other processors, the OS kernel, and even virtual machines by abusing fill buffer content in Intel CPUs. The fill buffer temporarily holds data during memory loads. Zombie load triggers faults and forces the CPU to speculatively access stale buffer contents before the CPU can invalidate the operation, leaking that previously loaded data via a timing side channel. It was disclosed by a collaboration of researchers, including Graz University of Technology again, and Worcester Polytechnic Institute. It has been demonstrated in labs with realistic attack scenarios, but again, no confirmed widespread public exploitation. However, it proved that even microarchitectural components like fill buffers are exploitable. Most Intel processors that have been manufactured since 2011 are affected, including Core and Xeon lines. Now we also have rogue in-flight data load. RIDL, RIDL. This allows data leakage across threads, cores, and even virtual machines via CPU internal buffers, think load ports. It exploits transient execution to read in-flight microarchitectural data from load ports, which are structures that temporarily hold data between memory and execution stages. It was discovered by joint participants from Vrije Universiteit Amsterdam, University of Michigan, and KU Leuven. It has been successfully lab tested with real-world leakage of keys and passwords from browsers, system processes, and guest virtual machines. Right now, I don't know of any published confirmed mass exploitation, but the risk is in cloud computing environments, and it's considered a very critical risk. So supposedly AMD and ARM are not vulnerable to it, but Intel CPUs across the generations are. And then we have Fallout. Not the game, but Fallout leaks data via the store buffer used during speculative stores and loads. Speculative memory operations use store buffers before commits, and Fallout forces the CPU to speculatively read from these buffers under attacker control, causing leakage from privileged memory locations. It was discovered by the same team that discovered Rogue and Flight data load, the Vrije University Amsterdam, University of Michigan, and KU Leuven. It's said to have been demonstrated in labs with high reliability, very repeatable, and especially in the multi-tenant and virtualized systems. We don't know anything about any public attacks at scale currently. These attacks impact most Intel processors released before the Ice Lake generation. That came out around 2019. Ice Lake introduced some hardware-level protections against speculative execution attacks. So if you're using an Intel CPU from before that, like Skylake, Kaby Lake, or is it Kaby Lake? I don't know. And Coffee Lake. It's likely vulnerable unless patches have been applied. AMD and ARM processors are not affected by this particular set of vulnerabilities because of differences in how their memory permission checks and speculative execution work. Specifically, Intel CPUs used to allow speculative execution to proceed before checking whether a memory access was permitted, which meant that even restricted data could briefly enter the pipeline and influence cache state, opening the door to side-channel leakage. But, in contrast, AMD and ARM CPUs perform permission checks earlier and more strictly. They block speculative access to memory regions if the access would eventually be denied, preventing unauthorized data from ever being loaded into cache, even speculatively. So this architectural difference is why attacks like Meltdown don't work on AMD and most ARM processors. There are hardware-level mitigations for these various attacks we've been discussing that out-of-order execution enables. Modern CPUs implement some mitigations directly in silicon, but not all protections are automatic, and many do require software support. Have the partitioning speculative paths. This mitigation technique isolates microarchitectural components, such as branch predictors, caches, and execution buffers, between different execution contexts, like user processes, kernel code, threads, or virtual machines. The goal is to prevent speculative execution behavior in one context from influencing or being observed by another. In many speculative execution attacks like Spectre, attackers manipulate shared CPU components like the branch predictor to train the CPU into speculatively executing in a certain direction. Then observe how the speculative path influences cache state. If these components are shared across security boundaries, an attacker running code in one VM, container, or process can potentially infer secrets from another. There's context-specific partitioning, where the CPU maintains separate state for different privilege levels or tenants, so that, for example, one VM's speculative execution history doesn't pollute or read the branch predictor or cache lines of another VM. And the flush-on switch, in some cases, instead of maintaining fully separate state, the CPU simply flushes microarchitectural structures, like the branch history buffer or TLB, when switching contexts, reducing the risk of cross-context leakage. And tagging or fencing speculative state. Some implementations track speculative data with tags and discard it more aggressively if it crosses certain boundaries. Examples of technologies are enabling this. Intel CET adds protection like shadow stacks and indirect branch tracking to reduce exploitation through speculative paths. While not a full speculative partitioning system, it complements it by hardening control flow integrity. And AMD SEV, Secure Encrypted Virtualization. This encrypts entire VM memory and introduces context separation to prevent hypervisor-level attacks, and in SEV-ES and SEV-SNP, it introduces CPU-level protections against speculative leakage between VMs. Intel TDX extends SEV-like protection to Intel platforms by providing isolated trust domains that are shielded from the hypervisor and other VMs, including speculative and microarchitectural attack surfaces. Now, these hardening measures are only available in newer CPUs. This hardware-level mitigation, including speculative path isolation, microarchitectural state flushing, and trust domain separation, are not retrofittable to older processors and are only implemented in recent CPU architectures that include security-focused features at that silicon level. The Intel 10th generation Ice Lake and newer CPUs began integrating more robust speculative execution barriers and architectural changes. The 11th generation Tiger Lake Intels and 12th gen Alder Lake Intels include additional protections and support for features like Intel TDX and control flow enforcement technology. Intel Xeon Scalable Ice Lake and later server CPUs include better partitioning for multi-tenant workloads in data centers. With AMD EPYC Rome 7002 series, introduced SEV-ES, Secure Encrypted Virtualization Encrypted State, and EPYC Milan 7003 series added SEV-SNP, Secure Nested Paging, which improves protection against speculative attacks by enforcing strict memory access control and isolating guest state even from the hypervisor. These CPUs implement speculative execution hardening at that silicon level, offering security boundaries that software alone cannot enforce. Application developers generally do not need to write or compile code differently to take advantage of these hardware protections. That's important to know. These features are implemented and enforced by the CPU, often below the level of the operating system even, or user space software. However, system administrators and platform engineers do have some responsibilities. Even if the hardware supports these features, they might be disabled by default or require explicit enablement through firmware or BIOS settings. Features like Intel TDX, AMD SEV, or CET must be enabled in system firmware. In some cases, enabling them may involve toggling secure memory encryption support, SMT mode or similar settings, and microcode updates. Many speculative execution mitigations require updated CPU microcode, which is delivered via BIOS UEFI updates or operating system microcode patches like Intel microcode or AMD 64 microcode on Linux, so we have to install those patches. Or operating system microcode packages like Intel microcode or AMD 64 microcode on Linux. And operating system kernel support, OS kernels like Linux equal to or greater than 5.x versions, Windows Server 2019 and beyond, need to support these CPU features and configure their use correctly. On Linux, SEV-TDX support may need to be compiled into the kernel and enabled via kernel parameters. And in virtualized environments, support must also be enabled in the hypervisor, like the KVM, VMware, or Hyper-V solutions. For SEV-TDX VMs, the hypervisor must present the appropriate feature flags and encrypt memory regions accordingly. Newer CPUs from Intel and AMD do have these hardware features that isolate speculative execution paths across contexts. So in these newer CPUs, these mitigations are ongoing. And developers don't need to do anything special to benefit from these if the system is configured correctly. System admins need to ensure firmware and hypervisors are updated and properly configured to activate these protections. Otherwise, these hardware mitigation features just sit there unused. But if you're using a system with an older processor, typically pre-2019 for Intel or pre-Ice Lake, or pre-EPYC ROM for AMD, your CPU does not include hardware-level mitigations for speculative execution attacks like Spectre, Meltdown, Foreshadow, or Rydal. These vulnerabilities can still be exploited on those platforms unless they're mitigated in software or at the system configuration level. So that is a concern, especially in environments where multiple users or processes share the same machine, like multi-user servers and academic or enterprise environments, and where virtualization or containerization is used, like cloud hosts or CI/CD build systems. Continuous integration, continuous deployment build systems for software developers and DevOps teams, etc. Though it's also a concern where sensitive workloads are handled, like key management, cryptographic operations, and proprietary data processing. Even though these attacks are complex and not always easy to exploit in the wild, they're powerful, stealthy, and very useful to advanced attackers. Think of APTs, government-sponsored attackers, and insider threats. You've got some smarty pants working inside. For older CPUs, the lack of hardware barriers means you're relying entirely on OS and software-level mitigations. On older CPUs, make sure you apply all OS-level security patches. Ensure your system uses a kernel version that includes mitigations. If you've got these older CPUs like KPTI, kernel page table isolation, retpoline, speculative store bypass disable, SSBD, and microcode-assisted patches. On Linux, check sysdevice's system CPU vulnerabilities path to see what is mitigated. Use the up-to-date microcode. Intel and AMD provide microcode updates that help mitigate some speculative vulnerabilities. On Linux, patches like Intel microcode or AMD 64 microcode should be installed. On Windows, this is typically handled via Windows Update or BIOS updates from the vendor. Disable simultaneous multi-threading, SMT hyperthreading, is an option, and you might just want, in scenarios where critical workloads are running, to do this disabling. Some attacks, like MDS and Rydal, exploit data leakage across hyperthreads. Disabling SMT can reduce risk at the cost of performance, though, and restrict untrusted code execution. Do not run untrusted binaries or scripts on older systems with shared access. And do use sandboxing technologies like AppArmor, SE Linux, or seccomp where feasible. And use trusted constant-time cryptographic libraries. This can help to prevent attackers from leveraging side channels that might be amplified by these speculative vulnerabilities. And consider workload migration or hardware upgrade. If you're handling regulated data like PCI DSS, HIPAA, or FedRAMP, using vulnerable CPUs without full mitigations may violate security requirements. You may be found to be out of compliance. Consider isolating risky workloads or migrating to hardware with native mitigations like Intel TDX or AMD SEV SNP capable CPUs. So older CPUs do remain vulnerable to a wide range of speculative execution attacks without hardware level protection. I mean, as long as they're new enough to be using out-of-order execution, of course. And there are still effective mitigations via OS, microcode, and configuration, but these often do come at a performance cost, and they require ongoing maintenance. So it's not always easy or efficient, doesn't always help productivity to enable these security options. So people use a lot of compensating control sometimes when they can't do these things. For highly sensitive or shared environments, migrating to a newer platform is the most robust long-term solution. Another hardware level mitigation is flushing CPU buffers. On context switches, CPUs with OS cooperation flush shared structures like TLBs, load store queues, branch target buffers. Requires firmware and OS support. Flushing CPU buffers like the TLB, load store queues, and branch target buffers is not something the CPU does automatically by default. It has to be explicitly triggered by the operating system at appropriate times. typically during context switches, privilege level transitions, or VM exits and entries in virtualized environments. To support this, both the CPU microcode, which is managed by the firmware BIOS, and the operating system kernel must have logic that issues the appropriate flush instructions. This coordination is necessary because not all CPUs support selective buffer flushing natively. It was added through microcode updates following the discovery of these speculative execution vulnerabilities. The OS kernel has to know when and how to trigger these flushes, especially during transitions between untrusted and trusted code contexts, like switching from a user process to kernel mode, or from one VM to another. If either the firmware or OS lacks support, flushing will not occur, and speculative data from one context might remain in CPU buffers and be exposed to the next context. However, flushing these internal buffers can reduce CPU performance, and this can be significant sometimes, particularly on systems with high rates of context switching, like web servers, databases, or virtualized hosts, things that we're using every day. This is because TLBs cache virtual to physical memory translations. Flushing them causes more frequent page table walks, increasing memory latency. BTBs help the CPU predict the direction of branches. Flushing reduces branch prediction accuracy, which increases pipeline stalls and mispredictions. Load store queue manages memory ordering and buffering. Flushing them introduces extra stalls and can disrupt speculative pipelines. Depending on workload characteristics, this can result in performance degradation ranging from a few percent to over 30%, particularly in multi-tenant or IO-heavy environments. So you see, this is all very complicated, so difficult sometimes to protect yourself, and that's why you have to weigh all these pieces and identify where you must use compensating measures. Now, because of the performance impact, these mitigations are often configurable. In the BIOS UEFI firmware settings, administrators may see options like speculative execution mitigations, indirect branch predictor flush, MDS protection, and SMT mitigations. In the operating system, these settings can be controlled via kernel boot parameters. Like on Linux, you've got spec store bypass disable on, mitigations, auto mitigations off, no spec store bypass, L1TF flush full, MDS full no SMT. On Windows, similar controls are applied via Windows registry settings, group policy updates, Spectre Meltdown patching status via Windows Update and PowerShell verification, like using Git speculation control settings. And by default, many enterprise and modern OS distributions enable mitigations if vulnerabilities are detected, but system administrators can override them based on their threat model and performance requirements. It's that juggling act. So flushing the CPU buffers does require coordination between firmware and operating systems. Microcode updates from CPU vendors are often needed to expose flush instructions, and the OS must decide when to flush based on context switching and privilege transitions. And because of the non-trivial performance hit, significant performance hit, these mitigations are often configurable via BIOS or boot flags, allowing administrators to tune or disable them in trusted environments. And then we have shadow copies of internal state. During speculative or out-of-order execution, the CPU may temporarily compute results before it's certain those instructions should actually run, like before a branch condition is resolved. To handle this safely, the CPU uses shadow copies of registers and internal state to store the results of these speculative instructions. These shadow copies are not part of the architectural state, meaning they don't update the program's visible state like general-purpose registers, memory, or flags until the CPU is certain the instruction path was correct. This happens in the reorder buffer. Results of speculatively executed instructions are held temporarily in non-architectural storage. Register renaming logic allocates new physical registers for speculative results instead of overwriting architectural registers, and execution units can perform calculations and store the results in these temporary registers until a branch is resolved. This matters for speculative execution because if the CPU predicts a branch direction and begins executing down that path, it doesn't yet know whether the prediction is correct. Instead of waiting, it performs the instructions speculatively using shadow copies. If the prediction turns out correct, the speculative results are committed to the architectural state, the registers and memory. If the prediction was wrong, the CPU discards all speculative results in the shadow copies, none of them affecting the program's final outcome. This mechanism allows the CPU to achieve high performance without breaking correctness, but it introduces side-channel risk. Even discarded speculative operations can leave microarchitectural traces, like changes in cache state, which attackers can exploit. The use of shadow copies is a mitigation technique to ensure that speculative operations don't directly corrupt or leak sensitive program state. They act as a temporary sandbox, ensuring architectural registers aren't overwritten by invalid speculation, and they help ensure speculative results are fully rolled back if a branch is mispredicted. However, shadow copies alone don't prevent side-channel leakage, because while they isolate the register state, they don't prevent effects on shared structures like the cache. This is why additional mitigations like buffer flushing, constant time programming, or speculative barriers are also needed. The deployment of this is fully handled by the CPU as part of its out-of-order and speculative execution engine. No user or developer intervention is required, and there are no BIOS or OS settings to control this directly. It's a built-in architectural feature of modern CPUs with register renaming support, that's virtually all superscalar processors since the 1990s. So shadow copies are temporary, non-committed versions of register values used during speculative execution. They allow the CPU to execute instructions ahead of time without corrupting program visible state. If speculation is invalid, the shadow copies are discarded, preserving correctness. And this mechanism is essential for performance, but not sufficient alone to prevent speculative execution vulnerabilities. So you need extra controls. And these protections are often only present in CPUs after the year 2018. They require microcode updates and operating system level enablement. So that was hardware level mitigations for these exploits that out-of-order execution enable. To briefly touch on operating system level mitigations, you've got KPTI, which we've already mentioned, kernel page table isolation. KPTI splits the virtual memory layout into separate page tables for user and kernel space. When in user mode, kernel memory is unmapped, preventing speculative access to kernel addresses. This is implemented in modern kernels. It's enabled by default in Linux 4.15 and beyond, in Windows 10 RS3 and beyond, in Mac OS 10.13.2 and beyond. Manual disablement of this is possible, but it's not advised. And then we have retpoline, return trampoline. That's the compiler level technique that replaces indirect branches with the speculative safe loop construct. It traps speculative execution to a benign path, preventing the CPU from jumping to attacker-controlled code during misprediction. It does require recompilation with retpoline-enabled compilers, and it's already widely adopted in operating system kernels, browsers, and high-risk binaries. And now we have the compiler and application level mitigations. These measures have to be actively implemented by developers or build systems. You've got SLH, speculative load hardening. It injects runtime masking into load instructions following potentially mispredicted branches. It's supposed to ensure that speculatively fetched data cannot leak secret values. It's implemented via compiler flags like speculative load hardening and Clang, and requires rebuilding binaries. And there's constant time programming, which enforces code paths and memory access patterns that don't vary with secret data. It works to prevent timing-based inference of secrets. This requires deliberate design choices and use of hardened libraries like OpenSSL's constant time APIs is recommended, and compiler flags like min-direct branch equals thunk. Replace vulnerable indirect branches with secure call sequences. This works to prevent speculative execution from jumping to unintended locations. It's used in GCC Clang builds for hardened code. Flag inclusion is typically a build system decision. Now, I just mentioned Clang twice. So what is Clang? That's a modern open source C++ Objective-C compiler that's part of the LLVM project, Low-Level Virtual Machine. It's known for being fast, modular, and providing detailed diagnostics that help developers write better code. Clang is widely used across many platforms, including Linux, Mac OS, and parts of Windows development. Now it's often used as an alternative to GCC, the GNU compiler collection, and many modern toolchains, including those used in security-hardened builds, rely on it for features like retpooling support to mitigate Spectre, for speculative load hardening, and advanced static analyses and code generation features. Clang is also the default compiler in Apple's Xcode, and it's popular in embedded systems, operating system development, and compiler research. So now let's talk about briefly the hypervisor and virtualization level mitigations for these exploits that out-of-order execution enables. Cloud and virtualized environments face unique speculative risks due to shared CPU cores and resources. VMM flushes on context switch. So hypervisors flush branch predictors, TLBs, and other microarchitectural state during virtual machine exits and switches to prevent data leakage across tenants. This is what they're working to do. It's implemented in KVM, Zen, Hyper-V, VMware XC, and requires patches and may reduce performance. And core scheduling, or SMT isolation. This works to prevent virtual machines from sharing physical cores or simultaneous threads in SMT hyperthreading with other VMs. It's for isolating speculative execution domains. It has to be explicitly configured, and some environments disable SMT entirely for security. Out-of-order execution and speculative execution might seem like low-level processor optimizations that only chip designers need to care about. But if you're working in cybersecurity, they are directly relevant to your day-to-day concerns. A strong grasp of these concepts is really helpful for a variety of reasons, like threat modeling is incomplete without it. When you're analyzing the risks associated with a system, whether it's a standalone server, a cloud tenant, or a browser running JavaScript, it could be helpful to ask, can a low-level privileged actor leak sensitive information by exploiting CPU behavior? Speculative execution vulnerabilities like Spectre, Meltdown, and their variants proved that hardware is part of your attack surface. These attacks do not rely on software bugs in the traditional sense. They exploit performance features of the processor itself to leak secrets like passwords, encryption keys, or cross virtual machine data. If your threat model assumes process, kernel, and VM boundaries are secure, you might be missing an entire category of attack vectors. And vulnerability assessment is not just about software. When you're assessing a system for vulnerabilities, knowing which speculative execution attacks a platform is exposed to matters just as much as checking for known software CVEs. You need to identify whether the CPU is susceptible to Spectre type or Meltdown type attacks. Determine if appropriate microcode updates have been installed. Check whether operating system level mitigations are active, like KPTI and retpooling. Evaluate whether speculative protections are disabled in BIOS for performance. If you're performing a security audit, penetration test, or compliance assessment, ignoring speculative vulnerabilities could mean missing real exploitable threats, especially in shared environments or on systems handling high-value data. And patch management and validation are more complex than they look. Most security patches affect software, but speculative execution mitigations span CPU microcode updates delivered via BIOS or OS packages, kernel updates for page table isolation and barrier instructions, compiler updates to generate REPLine-safe code, and runtime configurations like boot parameters and SMT settings. As a cybersecurity professional or systems administrator, it's not enough to ask, is the system patched? Instead, you also need to ask, is the correct microcode loaded? Has the OS enabled mitigations at runtime? Are compiler-level defenses in place for critical binaries? What's the impact on performance, and is it acceptable for the workload? In other words, it helps to know how to verify that speculative mitigations are actually in effect, and to understand the trade-offs involved. As we've talked about, performance versus security are two things that fight with each other throughout everything, as you'll continue to see more of the deeper you dive into cybersecurity studies. Secure coding now includes microarchitectural awareness. It used to be that writing secure code mostly meant avoiding logic bugs and input validation flaws. But in the post-Spectre world, secure coding also means thinking about how code interacts with the CPU pipeline. For example, are you writing code that conditionally accesses secrets based on user input? Are you using lookup tables like S-boxes that vary based on secret values? Could speculative execution leak secrets even if your logic is correct? Developers are now helped by understanding concepts like constant time programming, ensuring timing and memory access patterns don't vary with secrets. Speculative execution barriers like elephants, preventing speculative access to sensitive memory. And safe compiler flags like min-direct branch equals thunk and m-speculative load hardening, even at the application level. Secure software depends on secure interactions with hardware. And cloud and multi-tenant security definitely demand special attention for cybersecurity professionals. In cloud environments, speculative execution risks are amplified. Multiple tenants, organizations, users, containers might share the same physical CPU cores. So we're increasingly finding that this scope broadens as we advance. That creates the potential for speculative cross-tenant data leakage, even without traditional VM escape vulnerabilities. As a security engineer or a cloud architect, it helps to know whether the platform supports core scheduling, VMM buffer flushing, or SEVTDC hardware isolation. To understand how hyperthreading SMT can allow one VM to extract data from another. To decide whether to disable SMT for sensitive workloads. And to ensure that high assurance or regulated data doesn't share hardware with untrusted workloads. If you're working with virtual machines, containers, or multi-user servers, speculative execution is no longer a theoretical issue. It's a practical isolation concern. As a cybersecurity professional, you don't need to memorize the details of instruction schedulers or reorder buffers, but you absolutely do need to understand what speculative execution is, how attackers can exploit it, what mitigations are available, how to verify if those mitigations are working, functional, and effective, and what risks remain even after patching. Because this knowledge allows you to make more informed decisions and give better guidance about system hardening, risk prioritization, and secure architecture, especially in environments where shared CPU resources or performance-critical applications are involved. So, out-of-order execution is one of the reasons modern CPUs are so fast. It lets them juggle instructions efficiently and squeeze every bit of performance out of the hardware. That speed comes at a cost. When combined with speculative execution, it can unintentionally expose sensitive data through subtle microarchitectural side effects. And this is not just a theoretical problem. Attacks like Spectre, Meltdown, Foreshadow, and others have shown how these features can be weaponized to read memory that should be off limits across processes, privilege levels, and even virtual machines. Going through this lesson, we've talked about the fact that hardware, operating systems, compilers, and applications all play a role in defending against these threats. And while newer CPUs have started to build in stronger protections, older systems still rely heavily on patches, configuration, and awareness to stay secure. As a cybersecurity professional, understanding how these CPU-level behaviors work and how attackers can exploit them enables you more with the power to spot hidden vulnerabilities in your systems, to make informed decisions about patching, architecture, and isolation, to guide developers and admins in applying the right mitigations, to make sure of what questions you're asking vendors, and to take a look at what your hardware scope is within your organization and whether or not that creates additional vulnerabilities. To evaluate hardware security when designing or auditing systems. Ultimately, security doesn't stop at the software level. You're very well aware of that now. The processor itself is part of your attack surface. Understanding out-of-order execution a little better from this lesson gives you an opportunity to connect these dots more and be better equipped to defend your processor and your organization.